final part. So, getting commutants. The final part of our study of the powers of chi-q is definitely somewhat speculative. We're going to get back to the formal derivative stuff I was mentioning in the previous video. So as we saw, we had this particular formula. For fixed z, the expression here on the right is a rational function of a and b with rational coefficients. Moreover, as we saw, if we formally differentiate both sides with respect to b and then multiplied through by b, that would be the same thing as applying the homogeneity operator with respect to b. Notably, in computing the Fourier transform of f2, we had to use this relation to deal with the q equals 3 case. There are two equivalent ways of viewing this formal differentiation. The first comes from, as we saw before, exploiting summation by parts to write this. And the second comes from the Fourier transform side of things, where we had sums of this form for some rational constant c not equal to 0, and it was constants of and expressions of these forms which emerged from our untangling analysis. When c is equal to 1, this geometric series is degenerate and only grows linearly in its upper limit, while for c not equal to 1, the growth is geometric. In this regard, we really are just taking a formal derivative. Indeed, if c is not equal to 0, or not equal to 1 as well, if c is not equal to 1, this should not be a 0, this should be a 1, this identity holds. And then if we take the formal limit of both sides as c goes to 1, we get what is precisely a formal derivative. It's the formal derivative of f of c, where f of c is equal to c negative v2 of t. At first, this might seem like a mere coincidence, but it's not. Earlier, we showed this identity, which is with the Fourier transform of q to the number of ones of z mod 2 to the big N. It's worth spending a moment to take stock in what's actually happening in this integral. If we fix t, note that our integrand is a locally constant function of a two-adic integer variable. In particular, will be locally constant modulo a, where a is whichever of these is smaller. It's either 2 to the n or t2, which is to say that f is locally constant modulo the maximum of 2 to the n, the absolute value of t. Because of this, our integral reduces to a finite sum. Here, the complex exponentials are all 2 power roots of unity. Because of this, we have the following remarkable result. Fix big N to be a non-negative integer, let t be in z2 hat, and let d denote the maximum of n and negative v2 of t. Let R be any commutative unital ring of characteristic not equal to 2, so that the polynomial x to the 2 to the d minus 1 splits into 2 to the d distinct linear factors in R of x. Then, this identity holds as an equality of elements of R. And all of this works purely by algebra because this locally constant function's integral simplifies to this sum, which makes sense because we're not in characteristic 2. So this proposition can be thought of as the next generalization of the ideas of frame theory. In frame theory, we worked using any metric completion of a global field, for example, the rationals, and we picked our completions so that our expressions continue to make sense. However, as we've just seen, we can go further. There's no reason to stop just at number fields. It's because the Fourier inversion formula holds by tensoring for when we're working over locally constant functions. This Fourier transform pair holds in a purely ring theoretic sense. In particular, we will be able to realize the Fourier series as an isomorphism of rings, and not just any rings, but of particular importance, rings of formal power series. Going back to the very beginning of our journey, let's consider this F series for chi-q. Now let's generalize it a bit by replacing that chi pq is a map from the two adic integers to the ring of all formal power series in the variables p and q with coefficients in z. As a ring of formal power series, we have two differential operators, derivative with respect to p and derivative with respect to q. Letting p be any polynomial in two variables with integer coefficients, we can then differential operators, and that gives a linear differential operator on this ring of power series. Moreover, for any individual power series, we get a linear operator on our ring by left multiplication. Putting all of this data together, we can take our ring of power series and upgrade it to a non-commutative Z algebra generated by P, Q, and the two differential operators, consisting of all linear differential operators on this ring. If A and B are two elements of this algebra, we'll then write A and B to denote the differential operator given by composition, AB equals A of B. To see the non-commutativity, let's let f of PQ be a formal power series with integer coefficients. Then the differential operator delta QQ, it acts on f like so. First we multiply by Q, then we differentiate with respect to Q, and we have to use the product rule. So in this case we get that. So since f is equal to applying 1 to f, and since this is the homogeneity operator applied to f, we then have that partial QQ applied to f is equal to 1 plus Q partial Q applied to f, and so the commutator of partial Q and Q is then equal to the identity operator. In addition, since partial Q and Q is not equal to 0, we then conclude that these two operators do not commute, and so these two elements of our algebra are non-commutative. And algebras of this type, generated by relations of this type, are known as Weyl algebras, and they are incredibly important in abstract algebra, as they are, in a sense, the simplest non-commutative algebras we know of. Classically, and here I'm pulling my notes from Coutinho's Primer of Algebraic D modules, let K be a field of characteristic 0, let big N be a positive integer, and let bold X denote a tuple of n distinct indeterminates, so that our ring of polynomials in the xn's over K is denoted by this. With respect to polynomial addition and scalar multiplication, K of bold X forms a countably infinite dimensional vector space over K. Then from that we can construct the space of its endomorphisms. These end K of K bold X. This is the vector space of all K linear operators from K of bold X to itself. Note that this endomorphism ring then becomes an algebra when we equip it with the operation of composition as its multiplication operation. Classically, the Weyl algebra arises as a particular subalgebra of this endomorphism algebra. For each n, let xn hat denote the multiply by xn operator on K of bold X, and let partial n denote the partial differentiation operator with respect to xn. Then for each n, the nth Weyl algebra over K, denoted an, is the subalgebra of the endomorphism algebra generated by these operators and those operators. By the convention, A0 is then defined to be K itself. As with most things in algebra, this definition can be generalized. Let R be a commutative unital ring, and let A be a commutative unital R algebra. Viewing A as an R module, let ln end R of A be the set of R module homomorphisms of A. That is, given any L in this space, we have L of Rx plus Sy is R of RL of X plus SL of Y for all Rs in big R, and for all X, Y, and A. And of course, L of 0 is 0, and L of 1 is 1. This space is an R algebra with map composition as its algebra multiplication operation. And in particular, given any L and any R, RL is then the operator on A, which first applies L and multiplies by R. And since L is R linear, this is of course the same as LR. Next, given any A and A, let A hat denote the operator which multiplies things by A. And also by a derivation of A, we mean a map in ln and R of A, which satisfies the Leibniz rule. In this case, we then have that a Weyl algebra over A of order n is a subalgebra of ln and R of A generated by these guys, and where these are any particular derivations that are pairwise commutative. Yeah. The notion of the order of Weyl algebra is my own terminology. I'm not an expert of these things at all. So if there is a correct term for it, please let me know. So the standard example of this construction is where it's almost exactly like the classical construction I gave for a Weyl algebra over a polynomial ring over a field, but now we just take the polynomial ring with coefficients in R, a general commutative unitary ring, instead of necessarily a field. Weyl algebras and algebras of formal power series provide us with a very natural setting for discussing F-series. Of particular import, they provide a rigorous way of justifying my tendency in my work of treating Q and other quantities as variables in their own right, as opposed to fixed scalars. So as an example, if we consider this polygenic F-series, if we treat the QJs as indeterminates rather than rational numbers, note that for each Z in ZP, the right-hand side is then an element of the ring of power series with rational coefficients in these P distinct indeterminates. The work we did in episode 7 showed that this F-series had a Fourier transform, one which depended on the values of the parameters being used. In particular, setting Q0 equals 1 and letting R equals 1 plus the sums of the QJs, and setting P hat to be this, we found that these were the two possible Fourier transforms of S, and it depends on the relation between R and dP. Yeah. So far, everything we're doing is almost purely algebraic, except for the frame compatibility condition. However, this can easily be dealt with by applying the purely algebraic notion of the I-adic topology, also known as the Krull topology on a module. Unfortunately, Krull, like Techmuller, was a Nazi, so your mileage may vary. So definition 160. Let R be a commutative unitary ring, let M be an R module, and let I be a proper ideal of R. For any non-negative integer n and any element k of big M, we write k plus I n m to denote this set, where it's k plus rm, where r is an in and m is an m. And we then define I0 to be R. The I-adic topology on big M, also known as the adic topology on M induced by I, is then the topology generated by this family of sets, all of which are defined to be open in this topology. Given a set M, a pseudometric on M is a map which satisfies all of the properties of a metric, with the one exception that d of xy equaling 0 does not need to not force x to equal y. So a pseudometric is a metric-like function for which there may be multiple points of distance multiple distinct points that live at a particular location and have distance 0 from one another. We then say a pseudometric is non-archimedean if it satisfies the ultrametric inequality, with equality when this is not equal. Otherwise, we say the pseudometric is Archimedean. The nice thing then is that the adic topology can always be realized as a pseudometric space. That is, it's induced by a pseudometric. And the idea is directly as what we were familiar with from p-adic analysis. The distance between x and y is c to the -1 times the supremum of the set of n greater than or equal to 0, such that x minus y is in IN-M. Here c is any real number greater than 1. This is then going to be a non-Archimedean pseudometric, and the topology induced by the open neighborhoods with respect to this pseudometric is then equivalent to the I-adic topology on M. Likewise, we can then get that depending on changing the value of C will just give us an equivalent topology, so we can just pick our favorite C, and then I'll just refer to that as the Adic pseudometric metric, and the proof is very straightforward. It's a useful exercise if you're not comfortable with this sort of thing, etc. And yes. So, now from the theory of rings, we have the following wonderful equivalences that consider an R module M equipped with the Adic topology induced by an ideal I, and let D be an I-Adic pseudometric on M. Then the following are equivalent. The intersection of the power of in to the m is from n equals 0 to infinity is just 0. The I-Adic topology on M is Hausdorff, and D is a metric. We then have the following lovely fact, which is that the I-Adic topology is going to be Hausdorff, and thus all of these things will occur when R is both Noetherian and is either a local ring or an integral domain. Since if we're working with something like a ring of power series or a global field, and as long as things are finitely generated, all of these work, and all of this is nice, and then we get that our formula here is in fact a metric rather than a pseudometric. And so of particular import is the fact that we can, much like with the p-adics, we can complete a ring with respect to an ideal. And so let R be a ring, and for simplicity's sake, let I be a maximal ideal of R. Then the completion of R with respect to I is defined by the projective inverse limit of R mod I to the n, and we define this as R hat of I. If you don't know what projective limits are, I'm not quite sure what they are either. Well, I am, but it's complicated. But just figure it out. So in particular, if R is a Noetherian integral domain, and I is maximal, then this is going to be a metric space. In fact, it's going to be compact and a metric space, and we can then make it into a non-archimedean metric space using the I-Adic metric. So delightfully, we already have the means to freely apply these concepts to F-series, and in fact, we've already been doing it for quite a while. And this is, again, it's the idea where we're replacing numbers with formal indeterminates. So as mentioned before, in general, we saw that the shape of certain types of non-foliated polygenic F-series, they look like this. Now let's manipulate this slightly. First here, we're going to recall that the number of zeros in the p-adic digits, we define it for any integer n, it's the total number of p-adic digits minus the number of all the p-adic digits which are not 0. So with this, we then have the identity that 1 over d to the n ends up being equal to 1 over d times n minus lambda p of n times this sum, times this product. And so when we go through all of this and distribute everything, we get the following expression. Now we perform a birational change of variables. x0 equals 1 over d, xj equals qj over d, and we get this. So, and here note that since n minus lambda p of n is going to be a non-negative integer, and for n greater than or equal to 0, we then have that for n, if we consider the partial sums of s, these are going to be polynomials in the x's with coefficients in z. Consequently, letting n go to infinity, we're going to have that S of z is a formal power series in these indeterminates with integer coefficients. So how to make sense in terms of frame theoretic convergence, we can make sense of the convergence as follows. Let R denote this ring, the polynomial ring, and then for each j, let ij denote the maximal ideal xj times R. Viewing R as a module over itself, we then have that the ij adic topology is the xj adic topology, and so an element of R a sequence in R converges in the x adic topology if and only if it contains arbitrarily large powers of xj. In particular, the completion of R with respect to ij is the ring of power series in xj where the coefficients of our power series are polynomials in all of the x's other than xj. And so that's what our elements have appearance like. We can then whip up an xj Adic absolute value, which captures the ij Adic topology on the completion by defining our function to be, our absolute value to be 2 to the negative vanishing degree of f at xj, where the vanishing degree of f at xj is the degree of the zero f has at xj equals 0, with this being infinity in the case that f is identically equal to 0, and this being 0 in the case that f is not vanishing when xj equals 0. With this, we can give yet another reformulation of frames, this time in terms of ring theoretic completions. So let R be a commutative unital ring, which is a Noetherian integral domain, and let X be a set. Then an R frame on X is a map, which we go from goes from X to the spectrum of R, which is the set of prime ideals of R, which sends X to the ideal Fx. I'm also thinking that perhaps we might want to map to the maximal ideals rather than prime ideals, but I just picked prime ideals because it looks more like a scheme, which is, again, where I'm thinking this is all going. So anyhow, for each x, let's let Rx denote the completion of R with respect to the ideal Fx. We then make Rx into a topological space by equipping it with the associated Adic topology. The image of F is then the union of all of those different completions, and then we can repeat all of our constructions previously verbatim. We then have that the space of compatible functions, C of f, is the R algebra of all functions f from x to I of f that satisfy the property that f of x is contained in Rx for every little x and big X. The algebra operations are pointwise addition and multiplication, while R acts on this algebra by scalar multiplication. As usual, we call this algebra the algebra of compatible functions, and we then say if any function we happen to stumble upon is compatible with f whenever it's an element of C of f. Finally, we say a sequence in C of f converges with respect to f whenever for each little x and big X, fn of x converges to f of x in the fx Adic topology on Rx. So with this, there are several avenues worth exploring. Determine what extent, if any, this is compatible with the idea of a scheme. To me, again, I'm not knowledgeable of this, very knowledgeable of this at all, but I can still say it looks a lot like specifying the stalks of a sheaf of rings on X, though note that X was not given to have a topology, and that in theory the stalks need not vary continuously in X. Nevertheless, I wonder if perhaps by using the rising topology on ZP or some generalization of it for ring theoretic completions or projective limits, it might be possible to equip X with a topological structure with respect to which an R frame on X can be realized as a sheaf of rings. Also, we have the issue of reformulating the definition of frames that I just gave in terms of locally convex spaces. Here, instead of locally convex spaces over a field, it looks like we'll need to consider locally convex spaces over a ring. In the case where R is a ring of polynomials over some coefficient ring K, it seems natural to use the various degree at zero absolute values associated to the indeterminants of R to then define the ring theoretic seminorms on R in a manner analogous to what we did in episode 7. Next, there's the matter of our work with the powers of chi-q. To see how this might be generalized, going back to our F-series S sub z with its Fourier transform, what this says is that we have an F-series of this shape with coefficients Cn and some global field K. We'll have a Fourier transform, provided that the Cn satisfies some properties. Using A to denote the set of all such F-series, we then have that A is an abelian group with respect to pointwise addition. It's also then going to be we can get a K-module structure by scalar multiplication. And our work with chi-q of R suggests that we can upgrade A to a ring with respect to pointwise multiplication, and then we get that A is a commutative unital K algebra. In this context, the Fourier transform is then an isomorphism of K algebras, which maps A onto A hat, where A hat is the algebra under convolution of the Fourier transforms of all of the F-series in A. As mentioned earlier, if we set Rm to be the nth partial sum of this Fourier series, we get that this is going to be a rational function in A and B, and so letting big theta B be our homogeneity operator, we can then apply, this operator would then have a Fourier transform, phi b hat, which acts on the Fourier transform of R, like so. That is to say, phi b hat acts on Rm hat by multiplying Rm hat by a factor of V2. Note that for a fixed t, we get that as n goes to we get this, and so as m goes to infinity, we then have that theta b hat of Rm hat as m goes to infinity is this, which then says that we can go from theta b, an operator on the space of F series, effect like R, and we can then map that to an operator theta b hat on the space of Fourier transforms. And so in particular, theta b of R would be, applying theta b of R would be the same thing as applying theta b hat to R hat, and theta b hat multiplies R hat by V2 of t. So what this then shows is that our operator on our algebra of F series has an isomorphic copy that acts on A hat. In this context, the z's, as I mentioned before, fade into the background somewhat. They manifest not in A itself, but rather in maps from ZP to A, given by evaluating our F series at a particular p-adic integer. So this is actually quite satisfying and not at all unexpected. Back in episode 3, when we started all of this, we noted that this functional equation here could be thought of as a parameterization of the exponential Diophantine equation that Baum and Santacchi gave for the periodic points of the shortened QX plus 1 map. That is, our work took an algebraic structure, an exponential Diophantine equation, and showed that said structure could be interpreted as the image of a map of a two-adic integer variable. In particular, we have a map from the rational two-adic integers, and we can kind of ignore the irrational ones because its elements correspond to diversion points. Much in the same way, we can think of this F series as a parameterization of a family of formal power series in the variables d-1, q0 through qp-1 with coefficients in, say, z. We then had two distinct possible shapes of Fourier transforms for such an F series, depending on whether or not the identity blah held true. In this case, also this I should set this to be equal to 1, and so I can delete the q0 here. So in this viewpoint, the case of equality could be seen as considering this quotient, where p is treated as a number here rather than indeterminate. Note, it remains to be seen whether a Fourier transform can be assigned to every element of such a power series space, after viewing them as the image of functions of a p-adic integer variable, or whether we need to consider a subring with conditions on the coefficients in order to get the desired Fourier theoretic behavior. But the point here is that we have the algebraic structure of certain formal rings of formal power series can be enriched with the isomorphism furnished by the Fourier transform, provided that we view these formal power series as maps out of ZP. Even better, we can further augment these rings by equipping them with the differential operators associated to their indeterminates. And the Fourier transform will then be an isomorphism not just of the underlying algebra A, but also of the associated Weyl algebras of differential operators. Studying these algebras as modules over their algebras of differential operators seems like a promising method of geometrizing Collatz-type dynamical systems into a context where higher-level techniques like homology and cohomology might be of use, particularly if there is a way to make those notions interact with our parameterizations using maps out of ZP. Now, while this might seem like a lot, in truth, it's really only the tip of the iceberg. One of the most fundamental properties of mathematical analysis, as an example, is that derivatives tell us something about the rate of change of a function. Classically, if I tell you a continuously differentiable function has a derivative which is identically 0, we conclude that our function is constant. However, this principle doesn't just fail in a periodic context, it fails spectacularly. So fixing a prime p, let's write a p-adic integer z in Hensel series form, like so. Then let's define a function on ZP which has the following effect. That is to say, it takes the p's, and it just spreads them out by replacing p with p squared. Then phi of a minus phi of b is this. And so we note that an minus bn is going to be 0 for all n less than the p-adic valuation of a minus b. And so in particular, this is the smallest value of n for which an is not equal to bn. And so in that case, we get this here. And here, critically note that since these coefficients are distinct elements of 0 through to p minus 1, their difference is necessarily co-prime to p. Absolute value of a minus b. So now just divide by a minus b and take the limit as a approaches b. Then this is by definition the p-adic absolute value of the derivative of phi and is equal to 0. So what we conclude is that phi is continuously differentiable with an everywhere 0 derivative, but however, phi is not constant. In fact, phi is injective. In classical p-adic analysis, the fact that such really pathological functions exist is considered problematic, and the standard way to get around it is to consider what are called strictly differentiable functions. Robert's book on p-adic analysis covers this. And more generally, the moral here is that sensible p-adic analysts stay away from functions that play around with the Hensel series representations of p-adic integers. So, obviously, we're going to do the unsensible thing and consider exactly those such functions. Normally, p-adic numbers and q-adic numbers have no interaction with one another when p and q are distinct primes. Despite this, we can proceed in the spirit of the above example to construct some particularly useful p-q-adic functions. The idea is simple. Throughout our work, we've been treating parameters like p and q as quantities to be changed on the fly. To that end, if you want to go from the p-adics to the q-adics, what better way to do it than to simply perform a change of variables and replace p with q? So to that end, I define psi pq from zp to zq. We take the Hensel series and we replace the p with a q. I call this the pq-adic transition map, or just the transition map. And we have the following characterization of these functions. Phi pq is uniformly continuous. In particular, it's Holder continuous with a parameter a log base p of q. And this inequality holds with equality if and only if, for all a and b, if and only if p is less than or equal to q. Phi pq is injective if and only if p is less than or equal to q, and is surjective if and only if p is greater than or equal to q. And phi pq is the unique rising continuous function satisfying these functional equations. The proof. So the proof is almost exactly like what we did with our weird differentiable function, except here we have to take into account the when we take the q-adic absolute value. Note that if p is less than or equal to q, then it is possible that because these two numbers both belong are between 0 and p minus 1, then their difference will necessarily be co-prime to q. On the other hand, so in this case that would make this equal to 1 over here. On the other hand, if p is greater than q, there will exist a and b for which this difference is a multiple of q. And so in general, we only have an inequality, and then we change from p to q using logarithms. But if it's the case where p is less than or equal to q, we get an equality, and so we have what we want. So now for injectivity and surjectivity, if p is less than or equal to q, the equality here then shows our injectivity. On the other hand, if p is greater than q, we can then, by doing just some basic algebra, we then see that a equals q and b equals p both get mapped to the same output by phi of pq, which proves that phi of pq is not injective when p is greater than q. For surjectivity, note that if p is greater than or equal to q, then for any q-adic integer y, observe that since yn is less than q, which is less than p minus 1, we can then construct this p-adic integer, which our transition map will send to y, and that proves the surjectivity. On the other hand, if p is strictly less than q, then this p-adic integer is not in the image of our transition map, and therefore the map is not surjective. Finally, from the definition of 5pq, we immediately have this, just write out the Hensel series of pj and pz plus j, and then for rising continuity, we compute 5pq's Vanderbilt. Of psi's functional equations, they will both f and psi will agree on n0, and since n0 is dense in ZP, f and psi q, because f and psi q are both continuous, will then be equal everywhere, and that proves the uniqueness. So, now suppose that chi is a function satisfying this sort of functional equations for all z and zp and for all j. Then, if we precompose chi by the L-p-adic transition map for any prime L, we then end up using the L-adic shift map to conclude that chi prime equals chi of psi Lp, then satisfies L-adic functional equations, which shows that the f-series of a p-adic integer variable will pull back to an f-series of an L-adic integer variable when we precompose them with the transition map. This then suggests the following. Let f be a k-frame on Zp, and let L be any prime number. If chi is f quasi-integrable, then there is a k-frame f prime on Zl, so that chi of psi Lp is f prime quasi-integrable. It seems natural to want to study f-series by taking advantage of this transition maps to do homological algebra things. But wait, we can go even further. Going back to that identity that gave us such a trouble in lemma 33, if we squint a bit, we get that the sum on the right is of the following shape. It's some functions fn of z times a function g, which we evaluate at the nth shift of z. The presence of the two-adic shift operator here is not accidental. As we saw way back in episode 3, the functional equations of chi q can be succinctly stated with the help of the shift operator, where hz2 is the branch of the shortened qx plus 1 map, which is determined by the parity of z. Since hz2 is a bijection, in fact a homeomorphism, of zq, we then have this formula. More generally, for any polygenic f-series chi of a p-adic integer variable with coefficients and terms in, say, q, there are bijections hj of q to q, such that such a relation holds. To proceed further, recalling our adjoint identity, observe that chi of theta p of z, we can write it like this, and in particular, if chi is quasi-integrable with respect to a particular frame with a given Fourier transform, we then just do our computation using our adjoint, and we end up with this thing, which in particular shows that let chi be quasi-integrable, and then have that chi of the shift map is quasi-integrable as well, and its Fourier transform, we get this, is this formula. Consequently, we can then define integration like so. And so another way of thinking about this is that the linear map, which precomposes functions with the shift operator, is then has as its corresponding map on the Fourier transform space, works like a multiplier. Now let's generalize phi theta p slightly by considering this operator, where instead of just summing everything directly as we do with theta p, we're going to give this a weight, where we give a weight of qj, where the constants are in a global field, k, the one underlying our frame. And then when we do this, we get the following formula for the Fourier transform of theta of chi, which is to say that this linear map theta induces the linear map theta hat, which pre-multiplies chi hat by p and multiplies by this thing on the space of Fourier transforms. So defining this, I then call theta hat the Fourier transform of theta. And the main thing to observe is that the Fourier transform of theta's nth iterate is just theta hat's nth iterate. And to find a Fourier transform of the n of theta n of chi, we just apply theta hat to chi hat n times. And when you do this, look at what we end up getting. This is a very familiar formula. When we have the case where p is equal to 2, and q0 equals 1, and q1 is equals q, this is precisely those pi hat functions from the previous video. So what we see is that the untangling phenomenon that arises from iterated application that we saw arises from iterated applications of generalized shift maps. And so for constants an and k, we then get the following Fourier transform pairs, and which we can then do our untangling as n goes to infinity, and we get that it looks like this, where f chi is this thing. This suggests that this formula is then a starting guess for a Fourier transform of this thing. Moreover, if there is a single complete valued field in whose topology this limit converges, we can then directly take the limit as n approaches infinity in the topology of k, and then we get the Fourier transform pair, which at the very least will give us a realization of this function right here as a k-valued distribution on ZP. Thus, what really matters is the shift operator. And the fun thing is that this operator can be generalized to the completion of a commutative, unital, Noetherian integral domain R with respect to a maximal principal ideal, I, generated by some element pi. And particularly we want to require that R mod I is finite. Then we have the I-adic shift map on Ri hat. It sends R to R minus R mod I divided by pi, where R mod I is our choice for a canonical representative of the value of R mod I. As an aside, I wonder if this can be further generalized to the case where I is not principal. Given two such pairs of rings and ideals, R I equals pi, R prime, I prime equals pi prime, we can then define transition maps, just like we did with our PQ-adic transition maps, where we've picked, where the J's are some enumeration of the canonical representatives of the equivalence classes of R mod I and R prime mod I prime. If we equip these two completions with their respective adic topologies, I would expect the transition maps to be uniformly continuous and be injective, respectively surjective, if and only if, depending on whether or not, depending on the size of the, I call these the residue fields relative to one another. In fact, since these completions are locally compact, in fact compact abelian groups, we can then do our Fourier analysis, and it basically works verbatim. And so this then suggests that we can study algebras of F-series by using a transition map to pull them back to an arbitrary Ri hat. So this is getting pretty broad, and it may be perhaps even almost functorial. And I would be really interested if someone much cleverer than I could see what could be done by studying F-series from this perspective. Working around with the stuff out with these complicated is immediate and obvious that what we're dealing with is some kind of algebraic phenomenon involving the interactions of the various indeterminants that I've been given. And as I've said, what's really nice about using the ring theoretic perspective is that it gives us a setting where the weird detail of mixing topologies or going from one completion to another, it makes sense because we're looking at it from a ring theoretic perspective, and in this case, the fact that we can use different completions of a global field or a number field to do stuff is just a special case of the more general construction. What would be really neat, though, is if we could find a way to make this work not just for completions, but for projective limits, because then that would take us into the world of profinite sets, which is eerily reminiscent of what Peter Schulze is doing with his condensed mathematics, where you have the idea as a condensed set is a functor from a category of profinite spaces to whatever object you're looking at, a ring, a group, a topological space, etc. And so this suggests that there might be something useful gained for studying the interactions of those two ideas. Again, the sky's the limit, and most people say to save the best for last, but I happen to have this ready, so this is the part that I'm most excited about. But there's still a few more ideas I have to talk about. I think I'll probably be doing two more parts of episode 8 before we'll call it quits. But that's this episode for now, and I hope you've enjoyed it, and see you all next time.